we studied uniform motion, and that's when you're going on a straight line path, you're not making any turns, and you have constant speed. Essentially, constant velocity. Now we're going to be studying uniform circular motion. Once again, that's when an object has a constant speed, but the object this time is going to be going in a perfect circular path, traveling in a perfect circle, not speeding up or slowing down. And what we're going to discuss today is how to calculate this object's velocity, how to calculate this object's acceleration, and how to calculate this object's force that it is experiencing. So today's lesson is on uniform circular motion. So let's start off by drawing a circle, and let's say we're following some object that's going in this circular path, and what we want to do is be able to calculate the object's velocity, the object's acceleration, and the object's force that it's experiencing. So we start off with velocity. If we want to measure the object's velocity, we know that velocity is equal to distance over time. So I could just easily calculate how fast it's going by marking out a certain distance, say from here to here. And if I measure that certain distance, x, and then I time how long it takes to go that little distance, t, and then I divide x by t, I get how fast it's going. So it's nothing really new there. If you want to know how fast it's going, you just have to do distance over time, but the distance is curved. But here's the thing. You normally don't just use a little segment of the circle. Guess what's a convenient distance to use when you're calculating the average speed? What might be a convenient distance to use, Dylan?
2 pi, or 360.
Okay, basically that would be the distance what?
Around the entire circle.
Around the whole entire circle. That's a convenient distance to use. There's a special name for the distance around the whole outside. Say it loud, say it proud, David. The circumference. So this good old average speed formula that we know and love, okay, just takes on a new look. It becomes this. 2 pi r, that's the circumference. There's that 2 pi Dylan's talking about. And that's the distance all the way around the circle. And then you just have to divide by the time all the way around the circle. But that's a special time, and it has the symbol capital T. Capital T is the time all the way around the circle, and it's referred to as the period. The time for one complete cycle. So there's the new look when we want to calculate how fast the object is moving when it's experiencing uniform circular motion. Now the other thing we have to establish is the direction. The direction of the of the object when it's going in a circular path. So I have a plastic plate here, and the plastic plate has a little lip to it, and what I'm going to do is take a steel ball and I'm going to roll it around. Let's see, we'll roll it the other way to correspond with my other diagram. I'm going to roll it around the plate, and as it's rolling around the plate, and let's say like when it gets to like this point right here, I want to determine what's the direction of its velocity vector at that particular moment. Which way is it actually traveling at that moment? At that particular moment, as the ball comes around the plate, basically, is it traveling like, this way? Is it traveling like that way? Or is it traveling like this way? And what I have devised is a brilliant way of using my awesome magic powers. And as the ball comes around the plate and gets to the lower point, I make the plate disappear. I make the plate disappear, and that way I watch how does the ball continue to move after I make the plate disappear. And once I see how the ball continues to move when the plate disappears, I know, oh, that's the way the ball was going in the first place at that instant of time. So I'm sure you would like to see this demonstration. So for our 2 o'clock stretch, I'm going to ask you to come to the front table here. You turn on the lights. And gather around. Oh, play around here and around it goes, around it goes. Where does it stop? No one knows. Keep watching the ball. You're getting sleepy. You love physics. Physics is your favorite class. Keep watching it. You're going to get a 5 on the AP exam. Okay, so I just hypnotized you without you even realizing it. So anyway, ladies and gentlemen, what I'm going to do now is, as it comes around and it gets right there, I'm going to make the plate disappear, yes? Ready? Watch carefully. Watch carefully. This is very tricky. All right, here we go. Okay. But that was funny, guys.
Oh!
All right, I made the plate disappear, yes?
I thought it was clever.
All right, thank you very much. So as the ball comes around and it gets to this point here, is it going to move like kind of like over to here? Is it going to move like straight? Or is it going to move like out that way? Which way is the ball going to go? Let's hear it for the curving around, going towards where it was going before. Curving around. Let's hear it for the straight into the little hole right here. Let's hear it for the going back. That way. Okay, so here we go. I hold the center down here just to kind of give it like some reinforcement here. Give it a little spin. Okay, here we go.
Yes!
Oh,
yes! That was sick.
And basically, which way did it go, folks? Straight. It ends up going straight this way, ladies and gentlemen. So at that instant of time, its velocity is this way. And there's a special name for that. That's called the tangential velocity. Because if you have a circle and the velocity is that way at that given instant, it's along a tangent line. So the velocity is along a tangent line, so it's called the tangential velocity. So basically, take your little stretch, we'll go back to your seat. So at this point right here, the velocity is this way, tangent to the circle. At this point right here, if you want to draw the velocity vector, it's tangent to the circle. It's going this way. at this bottom point right here, it's going this way. If I just drew it at some point up here, the velocity vector is tangent. So we now know the direction of the velocity, and if we want to calculate the magnitude of the velocity, how fast it's going, then we use good old distance over time, but it has a new look. 2 pi r over the period t, where r is the radius of the circle. So 1 down, 2 to go. Now we have to discuss the acceleration. Now acceleration is kind of a tricky thing because we already established that we're studying uniform circular motion, which is constant speed. So at first you might be thinking, well, if it's going with a constant speed, it's probably not accelerating at all. But the truth of the matter is, even though it has constant speed, it's constantly changing its direction. Look at that velocity vector. The direction is always changing. And if the direction is always changing, technically the velocity is changing. And if the velocity is changing, it's technically accelerating. So to help us better understand this, we need a handy-dandy accelerometer. This is a liquid accelerometer. It's like the skinniest little fish tank that you've ever seen, yes? But instead of having water in there, there's like red food coloring in there, and basically we could see the liquid inside. Okay, so basically if we go ahead here, and draw the accelerometer, bless you, and inside the little tank, there's red liquid. Now, the red liquid stays horizontal like that if the accelerometer is at rest or moving with a constant velocity. But if I accelerate the accelerometer to the right, like this way, here, due to the inertia of the water, if I move the whole accelerometer this way, the water here at rest wants to stay at rest. So if I move it this way, the water wants to stay back here, but it can't because it's locked inside that container. So where does it all slosh to due to its inertia? Towards the back, yes? And when the water sloshes, you know that you're accelerating. So if I run to the right of the room, you'll see the water start to bank. Ready, set, go. Did it bank a little? And if I run this way, ready, set, go. And notice as I was decelerating, what was it doing?
It wants to stay in motion.
Pardon?
It wants to stay in motion.
Yeah, it wants to stay in motion, so it banked the other way. So, keeping that in mind, let's go back to our circular motion. Yes? I'm going to hold the accelerometer out, and I'm going to put it in uniform circular motion. And let's see if the tilt of the water can help us with the direction of the acceleration. So I'm going to try to go, for the most part, with a constant velocity, spinning in a circle. And for the most part, what's the water doing? Staying flat, which tells us it doesn't appear to be accelerating. And we knew it wasn't accelerating in the tangential direction, because tangentially it's not speeding up or slowing down. So at first we're like, I told you so, constant speed, it's not accelerating. But it is changing direction. So what if I turn the accelerometer like this? Yes? And I faced it inward. Now as I go and put it in a circular path, look what the water does. Now, look at the diagram on the board, the lower one. Look what's happening here. And answer the question in your mind, which way is the acceleration? Inward or outward? It's tricky. Again, look at the board there before I get too dizzy here.
Inward.
Okay. If the water is bent this way, the acceleration is in the opposite direction. So if the water gets banked to the outside, which way is the acceleration? Inward. It's an inward acceleration. And there's a special name for that. It's called centripetal. The acceleration is towards the center. And it's given a little C subscript, C for centripetal. And the centripetal has a P in the middle of the word, centripetal. So the acceleration at this point here is towards the center. Now, if you want to calculate the acceleration, you might be thinking, oh, let's use our acceleration formula. Vf minus Vi all over t. But the problem is, we're studying uniform circular motion, where objects aren't speeding up or slowing down. So if we were studying a car going around a circular track, and they had their cruise control set on 55 miles per hour, then their initial velocity would be 55, and their final velocity would be 55, and at first you would think, oh, the acceleration is 0. But yet with the accelerometer, we just saw how there really is an inward acting acceleration. The problem with this formula, it doesn't take into account direction. Velocity is really a vector quantity. Sometimes physicists put a little arrow above the symbol like this to remind themselves that these are vector quantities that have direction. And just like with vector addition, where you can have a 3 vector and a 4 vector equal a 5 vector, 3 plus 4 equals 5, yeah, when they're at right angles to each other. Well, when you're subtracting 55 miles per hour in one direction and 55 miles per hour in another direction, and you do vector subtraction, you don't necessarily get 0. The good news is, we're not going to have to monkey around with vector subtraction. Yay, because that's a pain. There's a derivation that shows a much easier way of getting that inward centripetal acceleration. It doesn't look intuitive. I know when I look at it, I'm like, what? But I've seen the derivation, and I've seen it match with experimental values to the point where I trust it, and hopefully you'll learn to trust it too. To calculate that inward centripetal acceleration, if you take the velocity that you calculated before, 2 pi r over the period, and you square it, and then you divide that by the radius, that, ladies and gentlemen, gives you the centripetal acceleration. So when you're you're dealing with circular motion, avoid using this formula because you don't want to have to deal with vector subtraction. Use the much easier v squared over r, where v is the tangential velocity and r is the radius of the circle. So going back, we discussed velocity, we discussed acceleration, and now we're discussing the force. Newton's second law of motion says if an object is accelerating this way, there has to be an overall force pushing it that way. Whatever the direction of the acceleration, that's the direction of the force. Well, the same thing goes with objects going in circular paths. If you have an object going in a circular path, if there's an acceleration towards the center, there must be a force acting on that object towards the center. So there's a force towards the center as well.
Would that be
It's called, not necessarily, depends on the situation. It's called the centripetal force because it's towards the center. There's that C word with the P in it, centripetal. Hey, again over here, if it's accelerating towards the center, there must be a force pushing it towards the center. Over here at the bottom, if it's accelerating towards the center, there must be an overall force pushing it towards the center. Over here, if there's an acceleration towards the center, there must be an overall force pushing it towards the center. And to calculate that force, that's nothing new. Law number 2 from a man named Newton. Let's go and get to our F net equals m times a. If you have a mass going in a circle experiencing an acceleration towards the center, and you want to know how much force is causing that acceleration towards the center, simply multiply the centripetal acceleration by the mass, and you get the centripetal force. So, in summary, if an object is going in uniform circular motion, the velocity is tangential, the acceleration is centripetal, and the force is centripetal. If you want to calculate the velocity, distance over time, but it takes on a new look. 2 pi r over t. You want to calculate the acceleration? New formula altogether to avoid vector subtraction, v squared over r. And if you want to calculate the force, F sub c equals m a sub c. Those are the 3 main circular motion formulas. Now, sometimes they're like combined. You could take the first formula, substitute it into the second formula. You could take the second formula, substitute it into the third formula. For example, a very popular look is like this. The centripetal force is equal to m, but instead of saying a sub c, what could you write in there? Excellent. Who said that? Good job, Jacob. F sub c equals mv squared over r. Very popular. You know, you'll see that in the textbook. They just combine the 2 formulas. Now, last but not least, I just got done teaching you that anytime an object's going in a circular path, it's experiencing a force towards the center. But what about like when you're the object? Let's say this room is a big gravitron ride, like one of those amusement park rides that goes in a big circle and you're spinning. If you're riding on the wall and the classroom is spinning around, yes, you're going in uniform circular motion, around and around and around. Which way do you feel like you're being pushed? It is such a strong feeling. I mean, if I lift up my head, it's like, oh, and then you know. Which way do you feel like you're being thrown? Outward. That's why so many people think that there's an outward force. There's actually a name for it. I don't want you guys to use this name because there really isn't an outward force. You feel like there's an outward force, but it's really not there. It's called the centrifugal force. But the real deal is the force is actually towards the center of the circle. Centripetal force. The only way I can explain this to you is if you were riding, let me just finish this off, in a real fast car. If the real fast car accelerates this way and pushes you this way and puts a force on you this way, which way do you feel like you're being thrown? Back. Are you being thrown back? No. Why do you feel like you're going back? Inertia. There is no outward force. It's just an inertia effect.
Always screw us. He is a crazy motherfucker.